Still going over the final exam. Problem 4D, as I goes from n down to I, down to 0 I mean, stopping at 1, then as j goes from I up to as far as n, but doubling every time. So this looks like an n and log n. Actually, it's not log n, you'll see. First, we're going to substitute k equal log base 2 of j, which means the log base 2 of 2j is k plus 1. So now the whole problem becomes this. We substituted, for the inner loop, we're writing it in terms of k. So the outer loop remains the same. All right, I'm going to need the other board over here. Here is the outer loop. I'm now using this rule here, which I wrote in advance. For any A and B, capital and capital B, if I take this outer loop here, or this loop, I go from A to B with I plus plus, then how much time does that take? This takes theta of B minus A time. All right, now the reason it starts at A, ends at B, and it goes one step at a time. All right, now let's apply this, let's call that a lemma, the AB lemma, or perhaps. We'll apply that not to the outer loop, but to the inner loop. And so the inner loop runs from log I to log n, so therefore that total there is theta of log n minus log I. Now, we're going to do it by integration. We'll let x be the continuous analog of I. So we integrate from x from 1 to n of log n minus log I dx. Well, the antiderivative of this is just constant, just this log n is a constant, so you get x log n. The integral of, well, this is not log I, this is log x here, is x log x minus x, so we subtract it. And what do we get? Evaluating from 1 to n log n minus n log n, then plus n here, and then subtract the values from x equals 1. So we get minus log x minus 1, this term disappears. And the dominant term is n, because the n log n canceled, we get theta of n. For E, and where I is decreasing while j inside keeps doubling only and up until it reaches I. All right, now k plus 1 is the base 2 logarithm of 2j because, because k is the log of j. Now here we'll replace this as k goes from 0 up to, well, we have to say k plus 1 less than log I because of this. And then we say k plus plus. All right, now, using the rule that when we increment here, starting from 0 going up to log I, going up one at a time, it's theta of this minus that. So log 2I minus 0, that's log 2I. Now we'll replace this by an integral using x as the continuous analog of I. Integral from x goes from 1 to n of the logarithm of x dx, and that's x log x evaluated from 1 to n, which is theta of n log n. All right, now let's go over to problem F. Here we have the I goes from 1 up to n, j goes from n down to 0, halving every time. Now you notice these two loops are independent, meaning that the index of this loop, which is I, does not appear anywhere as a parameter of the inner loop, which means these two loops run independently, which means we can multiply the time complexities. This one is theta of n, this is theta of log n, so the answer is theta of n log n. That was simple. Now we'll go to G. G uses a square root. I starts at n, stopping before 1, and you take the square root of it at each step. Now we'll let j be the log of I, which means that j over 2 is the log of the square root of I. Replacing these, when j is equal to j over 2 there. The interval j goes from log n down to 0. Now, we know that when we have every time, we get the logarithm of the beginning. So we get the logarithm of log n. So it's theta of n of log n, not n log n, but log n. All right, let's do 4h then. We start with the problem here. It actually is only one line. And I squared is less than n. But now we can replace that by the condition that I is less than square root of n. Which means that I is going from 1 to the square root of n. So it's theta of the square root of n minus 1 to theta of the square root of n. That's the answer. Now we'll do problem 5. Starting with problem 5. It's to determine the time complexity of these subprograms. So the first one, A, is we have f of an integer. If f is less than 2, we return 1. If otherwise, we return f of n minus 1 times f of n minus 1. We replace that by the recurrence. F of n is 2 times f of n minus 1. Now the plus 1 is justified by saying that it takes at least one time step to go through to set up the recurrence, for the program to call the other for itself twice. All right, so let's go over to here. We'll make the substitution that m is 2 to the n, which means n over 2 is 2 to the n minus 1. All right, so f of n is g of 2 to the n. We're going to make g of n equals f of n, which is g of 2 to the n. F of n minus 1 is g of 2 to the n minus 1. So I repeated that here. G of n over 2 is g of 2 to the n over 2, which is g of 2 to the n minus 1, which is f of n minus 1. And now we take the original recurrence here. F of n is 2 times f of n minus 1 plus 1, replacing this by g of m, and this by g of m over 2. So by the master theorem, we get that g of m is theta of m. But since m is 2 to the n, then it's theta of 2 to the n. All right, let's look at the next one, 5b. Well, here we have a program called hello, subprogram. And if n is at least 1, then we're going to call hello n over 1, n over 2. But if n is at least 1, then we go all the way from 1 to n of saying hello. So that takes linear time. But then after that, we recursively call hello n over 2 twice, which means the recurrence is, let's say capital H is the amount of time it takes to execute hello. It takes n steps here, plus 2 times the number of times it takes to execute hello of n over 2. By the master theorem, this is theta of n log n time. All right, now let's go to problem 6. Here the question is, which of these 3 problems is known to be NP complete? So for example, if the problem is P, since we don't know whether P equals NP, we don't know for sure that it's NP complete. So the answer is false. All right, now the first one, 6a, that's nothing but the traveling salesman problem. All right, now 6b is just placing figures into a table or a rectangle. Now this particular game, Pentominoes, you can buy in a toy store. And you could, if we have a solution, that solution can be represented in polynomial time. Usually there's a picture in the box that tells you what it is or you could find it. So this is definitely in the class NP. Now it's known to be NP complete because the subset sum problem can be reduced to it. So therefore it is NP complete. All right, now the next question, given a graph and given 2 points, does there exist a path between them of weight no more than d? Well, you can figure that out using breadth first search, which takes linear time. And so the answer is Yes, linear in the number of edges, so that is polynomial. All right, now let's look at problem 7, which I've crowded over here. Here, it's assorted the first I elements, but we're looking for the I plus first element here. For that, we iterate through all the remaining elements, and we swap, whenever we find one smaller than what we had before, we swap it into this position. So that's the selection sort algorithm. Those people who said bubble sort were not correct. I know the bubble sort has swaps in it, but this is not bubble sort. Now, problem 8 is inherently easy to understand. We're given an out-neighbor list for a directed graph, and we're supposed to or actually it's an array of out-neighbor lists, and we're supposed to construct an array of in-neighbor lists. This is the way you should represent a directed graph if the number of edges is larger than the number of vertices, but not a great deal larger. All right, so now I'll do this online, which means I might make a mistake. On the other hand, if I have an answer here and it disagrees with what's on the web page, the one on the web page should have been checked carefully, so that's the one that's right. All right, so we'll start with from 0, there's an edge to 1 and to 12. So we put 0 here and 0 there. For 1, there's an edge from 5 to 19. So we put 1 here and 1 here. That should be clear. Now from 2, there's an edge from 5 to 14. So for 5, we put a 2. And for 14, we also put 2. All right, from 3 to 9, so 9, we write 3. There, just the opposite. From 4, there's an edge to 7 and 15, so we'll put for 7 and for 15. And for 5, there's an edge to 4 and 10, so we'll write 5 here and 5 here. And 11, we'll put a 6. And 7, for 16 and 18, we'll put a 7. And then for 17, we put an 8. And for 9, for 8 and 15, we put a 9. And let's see, for 4, we put a 10. And for 7, we put an 11. And for 2 and 6, we put a 12. And for 1 and 2, we put a 13. And for 11, we put a 14. For 17 and 18, we put a 15. Uh-oh, we're running out of space. There we go. For 16, well, no, nothing goes to these others, but 3 and 5, 19 goes to 3 and to 5. So we're done. There we go. 1, 2, 19. Like I said, I could easily have made a mistake. That is so. The one on the web page is the correct one. All right, now this one is, I told you that I would expect you to know the code for the Floyd-Warshall algorithm, which is the all pairs shortest path problem in a directed graph, which may have cycles and which may have negative weights. And it's a theta of n cubed time graph, which is about as long as you expect to take. What we're going to do is we'll start by initializing. We'll assume that wij is the weight from ij, which could be infinity. And fij, we're going to actually construct this value. It'll be the minimum weight from I to j. And the back pointer, which is the name of the vertex, is the last vertex before j on the minimum path from I to j. And that's called the back pointer because if you get there, you follow the back pointer in order to reconstruct the path from I to j. All right, now, initialization, f will be the minimum weight, so initially it'll be the weight of just one edge, which could be infinity. However, the weight of the shortest path from I to I is an empty path, which is weight 0. So we have to initialize that just in case it came out to be infinity someplace else. Now the back pointer of the to j is defaults to I. Well, that's not going to last. All right, now how do we do this? We have to iterate, we have a triple loop, and we have to remember that what we're trying to do is do a relaxation where we have I, j, and k, and if we have the path from I to j and a path from j to k, and then we also have a path from I to k, this new path. So let's remember what we're doing. When we have a relaxation here, we are assuming we already have a path from I to j and from j to k. Now, of course, those could be the infinity or non-existent paths. What we do is we check the cost of a path directly from I to j, and we already have one of those. But it might be possible to do better by going through j. Now, one of the things about the Floyd-Warshall algorithm is whatever path we have from there to there definitely does not include j because of the way the loops are set up. So we're now getting the first opportunity to get a better path that goes through j. We may or may not get a better path. And so what we're going to do here is first the iteration for j equals 1 to n, and then for I equals 1 to n, and for k equals 1 to n. Now, the one that's in the middle for relaxation must be the outer loop. All right, so now what we're going to ask is this. We're going to check the values. So, well, I'm going to set this up to be a temp. The temp value is f of ij plus f of jk. Now, when I said there is no path which has j in the interior, that still allows paths from j to the end. So in other words, a path from I to j may exist, but there'll be no j in the interior here. And likewise, no j in the interior of that or in the interior of that. Now, if this is true, if temp is less than the current value of I, k, the value, then we're going to replace this. Fik is equal to temp. But we're also going to replace the back pointer. All right, let me briefly explain why. We're interested in the back pointer. Now, there could already exist a back pointer here, a back pointer jk, and a back pointer ij, and there was already a back pointer from I to k. However, remember, this new path, which goes through j, is shorter than this old path. And so we don't want to have this as the back pointer, but rather that one. So the new back pointer is the old back pointer of the path from j to k. Now that could possibly be j itself. And so this is the code for it. I don't have all the correct squigglies in there, but you can tell.